Welcome to another video lecture. In this video lecture, we are going to discuss about the steady state response analysis of the control system. Let us first discuss a closed loop control system, and we will calculate first the error ratio, and with that we will calculate the steady state error. So a closed loop system consists of input Rs, which is applied to a summing element. Then we have open loop gain Gs, and we have a output, controlled output Cs, feedback gain Hs. There is a negative sign here, this is a positive. Now in this closed loop control system, here we have a error signal Es, which is the difference of these two signals. One is the input signal and one is coming from this feedback network Hs. Now to calculate this error ratio, first let us define this Es. Es is the error signal. It is Rs minus, let us assume that there is a signal Bs, so this will be Rs minus Bs. Now the Bs signal is nothing but Hs, which is the feedback signal, multiplied by Cs, since a signal Cs is coming, so gain is multiplied by the incoming signal is the output. So this Bs is nothing but Hs into Cs, and this Cs is nothing but this Gs signal multiplied by Es. So let me write it here. Cs is Es into Gs. So I will write Cs first here, and then I will put this value of Bs in this. So finally I can say this Es is equals to this Rs minus Hs into Es into Gs. Now I can take this value on this side, so I can say Es, I am taking common, so this will be 1 plus GSHS. GSHS is equals to Rs. So finally the error ratio Es is equals to Rs divided by 1 plus GSHS. So this value Es is known as the error ratio. This is known as error ratio. Now to calculate the steady state error, let me first define what is steady state error. In the first order system, we have already seen that the output of the first order system is exponential Ct versus time, and this is, let us suppose this is the steady state value. So the response of the first order system is exponentially increases, and at t tends to infinity, it approaches or it reaches the steady state value. So there is a difference between there is always a difference between the steady state value and the response of the system when system stabilizes. This difference is known as the steady state error, ESS. Now to calculate this steady state error, is equals to it is basically error when limit t tends to infinity. So this steady state error is nothing but Et when limit t tends to infinity. Now if I'll apply final value theorem in this, I know what is final value theorem, that it is. So if I will apply final value theorem in this, I'll get ESS equals to limit s tends to 0 s into Es. So steady state error is nothing but limit s tends to 0 s into Es, where Es is the error ratio. So next we will discuss steady state error for different type of input signals. We already defined what is a steady state error. ESS is equals to limit s tends to 0 s into Es, where Es we have already defined. This is Rs, which is the input signal, divided by 1 plus Gs into Hs. So ESS is equals to limit s tends to 0 s into Rs divided by 1 plus Gs Hs. So this is the steady state error. Now let us discuss different type of inputs. We have already discussed what are the different type of inputs which we can apply to a control system. First we are taking a unit step, or rather I said say a step input. For a step input, the value of Rs is suppose A by S, where A is the magnitude of the signal, and we know that for a unit step signal ut, the Laplace transform is 1 by S. So for this signal A into ut, the Laplace transform will be A by S. So we have taken this signal, step input signal, and for this step input signal we want to calculate the value of steady state error. Now for this input, we will put this value Rs in this expression here. So for this step input, the value of steady state error is equals to limit s tends to 0 s into Rs. Now Rs is 1 by A by S for the step input, divided by 1 plus Gs into Hs. Now this s will get cancelled here, so this will be, and this limit will be applied only for the term which contains s. So this will be ESS equals to A by 1 plus limit s tends to 0 Gs into Hs. So if I assume this to be limit s tends to 0 Gs Hs, let us assume this equals to Kp, which is known as the position error constant. Then the expression for ESS is equals to A upon 1 plus Kp. So for the step input, the steady state error comes out to be A divided by 1 plus Kp, where Kp is the position error constant. The next input which we are considering is the ramp input. So the next input is ramp input. So in this case, the value of Rs will be equals to A by S square, since the Laplace transform of ramp signal is 1 by S square, and we are considering this with the magnitude A. So the value of Rs is A by S square. In this case, the steady state error ESS is equals to limit s tends to 0 this Rs, s into Rs is A by S square divided by 1 plus Gs Hs. Now in this case, this one s will get cancelled, so this is limit s tends to 0 A by S plus S into Gs Hs. Now when we apply this limit s tends to 0 in this, this will become 0, and this will become limit s tends to 0 S Gs Hs. Let us assume this to be equals to another constant Kv. So I am assuming limit s tends to 0 S into Gs Hs. Let us assume this to be Kv, which is known as the velocity error constant. Then the steady state error in this case is equals to limit A by Kv. Sorry, limit already have applied. So this will be A by Kv, where Kv is limit s tends to 0 S into Gs Hs. So for the ramp input, the steady state error comes out to be A by Kv. Let us discuss for the third type of signal, which is the parabolic input. So parabolic input. For the parabolic input signal, the value of Rs is A by S cube, since the Laplace transform of parabolic signal is 1 by S cube. T square by 2 is the signal, so the Laplace transform of T square by 2 is 1 by S cube, and we are considering with the magnitude A, so this Rs is A by S cube. Now for this signal, the steady state error ESS is equals to, again, limit s tends to 0 S into Rs. So Rs I am applying 1 by S cube divided by 1 plus Gs Hs. Again, this 1 power of S will cancel here, so this will be limit s tends to 0 A by S square plus S square Gs Hs. Now again, this S square term will be 0 when I will apply s tends to 0, and this term I am assuming that this to be another constant, acceleration error constant. So let us assume limit s tends to 0 S square Gs Hs is another constant Ka, it's known as the acceleration error constant. So finally ESS will be equals to A by this Ka, where Ka is the acceleration error constant. So for all these three type of inputs, step input, ramp input and parabolic input, we have defined and calculate the error constants, different error constants.